Hello everyone, my name is Twinkle Kothari. I am a research assistant at UTA Research Institute. I am a second year PhD student at UTA. I would like to present my work on design and analysis of reinforced I-beam lattice with enhanced energy absorption. The beam lattices can be divided into two types based on the deformation. First is the stretching dominated, the second is the bending dominated lattice. The stretching dominated lattice has high strength to weight ratio, while the bending dominated lattice have high energy absorption. The stretching dominated lattice fails mainly because of buckling, while the bending dominated fails because of joint yielding. These beam lattices are lightweight. They have high stiffness to weight ratio, they have high strength to weight ratio, they have high specific energy absorption, and they are highly customizable. They are used in mechanical components. This is aircraft part that GE Aviation recently built. Well, how can we improve stiffness, yield strength, and energy absorption simultaneously? I-beams. Beams with I-shaped cross-sections called the I-beams. They have better bending stiffness and have high strength to weight ratio. This is what a full-scale FE model for a conventional circular beam lattice would look like, and a circular conventional unit cell is shown with the stress-strain curves here. The three lattice designs considered have cross-sections. First circular, second is the I cross section, third is I cross section with reinforcement at its joint. This is what the dimensions for each cross sections looks like. The three lattice designs are printed using stereolithography with durable resin, and quasi-static test was done using the MTS testing machine. The experiments conducted on the MTS compression machine provides the stress-strain curve on the right here. We can see the process of compression from the three pictures of the MTS machine. The area under the stress-strain curve is called the energy absorption. Here in this case, we see that the maximum energy is absorbed by the reinforced I-beam lattice. We see a 247% increase compared to a circular beam lattice. The simulations is such that the beam lattice is kept between two rigid plates and a downward quasi-static load is applied on the upper rigid plate. We can see the crushing simulation on an I-beam lattice on the right here. The simulations done on reinforced I-beam lattice agrees well with the experimental curves. In the linear region where the elastic deformation happens, this is what the stress distribution looks like. After the linear elastic deformation, joint yielding occurs, and this is what the stress distribution looks like. After the joint has yielded, the sectional collapse occurs. This did not exist in a conventional circular beam lattice, but here the web of the I section collapses, and we see that the energy absorption, that is the area under this curve, increases drastically in reinforced I-beam lattice. After the sectional collapse of the I section, one by one all of the webs of the I section collapses, and once that happens, a densification point is reached and the material continues to undergo deformation after that. And so it can be said that stress distribution in the flanges and the web of the I section beams reduces the stress concentration at the joint of the beam lattice, and therefore the beam lattice with I section and the I section with reinforcement has higher yield strength over a circular conventional beam lattice. Second is a new multi-stage energy absorption mechanism that involves the sectional collapse of I-beam is introduced. And third, reinforced I-beam lattices have approximately 250% improved energy absorption than a conventional circular beam lattice. Thank you.